Welcome all. Today we are going to start with the fourth unit, that is sequential logic circuit. In this unit we are going to study regarding the flip-flops, resistors and counters. First we are going to study regarding the flip-flops. So we will start with the sequential circuits. In sequential circuit, the timing parameters needs to be considered. The output of sequential circuit depends on the present input, previous output and the sequence in which the inputs are applied. In order to provide previous input or output, a memory element is required in this sequential circuit. So there are two terms, present state and the next state of the sequential circuit. Present states are represented by a Qn. The data stored by the memory element at any given instant of time is called as the present state of the sequential circuit. Means this is the state of the output of sequential circuit before applying any inputs to the circuit. And the next state, which is represented by Qn plus 1, this is the state of the output of sequential circuit which operates on the external inputs. Means we get this state after applying the inputs to the circuit, by which the new outputs are stored by the memory element. Now we will see the comparison of combinational circuit and sequential circuit. This we already studied in the initial part of the unit 3. Again we will revise it once again. In combinational circuit, the output at any instant of time is dependent only on the input present at that instant of time, whereas in sequential circuit, output at any instant of time is dependent on the present input as well as past input or output values. As the output is dependent only on present input, the combinational circuits do not need any memory, whereas to store the previous input or output values, the sequential circuit requires memory element. The clock input is not necessary in case of combinational circuit, whereas the clock input is necessary in case of sequential circuits. The examples of combinational circuits are adders, subtractors, code converters, comparators, etc., which we have already studied in the previous chapter. Whereas the examples of sequential circuits are flip-flop, shift registers and counters, which we are going to study in this unit. So let us start with the 1-bit memory cell. What is 1-bit memory cell, which is also called as a cross-coupled inverter? The flip-flop is known as a basic digital memory circuit. Means the flip-flop can store a 1 bit of data in it. It has two stable states, namely logic 1 state and logic 0 states. We can design it using NOR gates or NAND gates. In this, a 1-bit memory cell is designed using NAND gates. Which includes two NAND gates. Both the NAND gates are going to act as an inverter, as both the input terminals of these NAND gates are shorted together and a common input is given. So with this structure, NAND gates acts as a inverter. We already studied this in universal gates. Hence the output of gate 1 is connected to the input of gate 2 and output of gate 2 is connected to the input of gate 1. Therefore, this circuit is also known as a cross-coupled inverter, as the output of this gate 1 is connected as input to this one and output of gate 2 is connected as input to the output of gate 2 is connected as input to the gate 1. This is how the outputs are cross coupled. Therefore, the circuit is known as a cross coupled inverter. Now you will see the operation of this memory cell. Assume output of this gate 1, that is Q, is 1. Hence B2 will become 1. As B2 is 1, the output of gate 2, that is Q complement, will become 0. As Q complement becomes 0, B1 will become 0, by which the output of NAND gate 1 will become 1. Hence Q continues to be equal to 1. Similarly, we can demonstrate that if we start with Q is equal to 0, then we end up with obtaining Q is equal to 0 and Q complement is equal to 1. So, if previously we assumed Q as a 1, we will end with the Q equal to 1 and Q complement equal to 0. And if we assume previously Q equal to 0, we end up with the Q equal to 0 and Q complement is equals to 1. So based on this operation, we can conclude that the output of the circuits, that is Q and Q complement, always complementary with each other. That means if Q is 0, Q complement will be 1, and if Q is 1, Q complement will be 0. They will never be equal with each other. If we found Q and Q complement both are equal, then it will be an invalid state for that circuit. The circuit is having two stable states. One is reset state, for which Q is 0 and Q complement is 1, and another is set state, for which Q is 1 and Q complement is 0. If the circuit is in reset state, then it will continue to be in the reset state, and if such circuit is in set state, then it will continue to be in the set state. This property of the circuit shows that it can store 1 bit of digital information, that is either 0 or 1. Therefore, it is called as a 1-bit memory cell. Now next we will see the latches. It is a type of storage device which has two stable state. It is different from flip-flop, but the latches and flip-flops both are similar because both of them are basically the bistable devices, that is devices having two stable states. The main difference between latch and flip-flop is that the method used for changing their states. We will see the methods which are used for the latches and flip-flops in the next lectures. In this lecture we are going to study the SR or RS latch, which can be constructed using NOR gate and which can be constructed using NAND gates. This is called as set reset flip-flop latch, as the output gets set or reset. Therefore, this latch is named as a set reset latch. Now we will see the SR latch using NOR gates. This is the SR latch which is constructed using two NOR gates. This is a bistable circuit having two stable states. It has two outputs, Q and Q complement, which are complements of each other. The two input terminals to this latch are set and reset terminal. The set terminal is named as S, reset terminal is named as a R, which are input to this latch. The two NOR gates are cross coupled. That means output of NOR gate 1 is connected to the input of NOR gate 2, and output of NOR gate 2 is connected to the input of NOR gate 1. The outputs Q and Q complement can be expressed in the form of Boolean equation as Q can be written as R plus Q complement, R plus Q complement and its whole complement, as this first NOR gate is having input as a R and Q complement. Again, output of NOR gate 2 can be written as S plus Q whole complement, as the NOR gate 2 is having two inputs S and Q. This is the circuit symbol of the SR latch, which is showing two inputs S and R and two outputs Q and Q complement. Now we will see the operation of SR latch. As the latch is having two inputs, there can be four possible combinations: 0 0 0 1 1 0 1 1. We will see the four cases one by one. In this first case, S is 0 and R is 0. So unless and until we know the second input of both these NOR gates, we cannot predict the output of the circuit. Therefore, here we have considered previously the output of this circuit. Initially we have considered the output is in reset state, that is Q is 0 and Q complement is 1. Q is 0, Q complement as a 1. So now we can have the another input of both the NOR gates. Another input of NOR gate 1 will be 1, as this Q complement is connected to the NOR gate 1. Another input of NOR gate 2 is 0, as the Q output of NOR gate 1 is connected as input to the NOR gate 2. So NOR gate 1 will have two inputs 0 and 1, and NOR gate 2 will have two inputs 0 0. So by putting these values, we get Q as a 0 and Q complement as a 1. So initially we have considered Q as 0, Q complement as a 1. After applying inputs, we get the same outputs, that is Q as 0 and Q complement as a 1. Means in case 1, previously we assumed the reset state. After applying input, we get the reset state itself. Again, if we consider the previous output is in set state, then also we get, by applying these input values, Q as a 1, Q complement as a 0. So in second case also, if the previous state is in set state, we get the next state as a set state itself. Therefore, for S equal to 0, R equal to 0, next state is the previous state itself. Therefore, output will not change, it will remain in the previous state itself for S equal to 0, R equal to 0. So we can say that output will not change, it will remain as it is for the S and R as a 0. Next, we will see the second case, S equal to 0, R equal to 1, which is named as a reset state. We will see why that is called as a reset. Now here, this is the circuit in which S is 0 and R is 1. Now here, as R is, we know the truth table of NOR gate. From this truth table we can conclude that output of 2 input NOR gate is 0 if at least one input is 1. If at least one input is 1. These are the 3 observations. Therefore, the NOR gate 1 is having at least one input as a 1, that is R is equal to 1. Therefore, output of NOR gate 1 Q will become 0. Now S is already 0, hence another input of NOR gate 2 will be 0 as Q is 0. So hence both the inputs of NOR gate 2 are 0, therefore Q complement will be 1 as per this truth table. As both the inputs are 0, output will be 1. Now hence, as Q complement becomes 1, another input of this NOR gate will be 1. Therefore both the inputs of NOR gate 1 are now 1. Therefore Q will be 0. For 1 1, output of NOR gate is 0. Thus stable output state of Q equal to 0 and Q complement equal to 1 is reached. As Q is 0 and Q complement is 1, this state is named as a reset state. This Qn plus 1 is the next state, and this Qn plus 1 complement is the complemented next state. Therefore for S equal to 0, R equal to 1, here S is 0, by mistake it is written as a 1. S is equal to 0, R equal to 1, we get Q0 and Q complement 1. Now next we will see the third case, S equal to 1, R equal to 0. This is the circuit diagram in which S is 1 now, R is 0. As S is equal to 1, output of NOR gate 2 will be 0, as output of NOR gate is 0 if at least one input is 1. Therefore output of NOR gate 2 is written as 0 as its one of the input is having input as a 1. Now R is already 0. Another input of NOR gate 1 is 0 as Q complement becomes 0. So both the inputs of NOR gate 1 are now 0. Therefore the Q will become 1. For 0 0, the output will be 1. Therefore Q is 1 now. Hence, as Q is 1, both the inputs of NOR gate 2 are 1. Therefore Q complement will become 0. For 1 1, the output is 0. Thus stable output state of Q equal to 1 and Q complement is reached. Therefore for S equal to 1 and R equal to 0, we get Q as a 1 and Q complement as a 0. Therefore this output state is named as a set state. Now in the last case, S is 1 and R is also 1. This is a circuit. S is 1, R is 1. As one input of each NOR gate 1 and NOR gate 2 is at logic 1, so output of both these gates will try to become 0 now, as at least one of the input of both the NOR gate is 1. Thus both the outputs Q and Q complement try to become 0 at the same time. This is not acceptable because Q and Q complement should be complemented of each other, as we find here both the outputs as a 0, which is not acceptable. So we should avoid this condition and it should not be used as it violates the basic requirements of latch. So for s equal to 1, r equal to 1, as both the outputs become 0, this state should be prohibited, so it is named as a prohibited state, or this condition is also called as a race condition, as both the outputs are racing to become a 0. So this is the summary of all the conditions which we have discussed earlier. This is our case 1. In which s is 0, r is 0. This qn and qn complement are the output state before applying the inputs, that is are named as a present state. This qn plus 1 and qn plus 1 complement, these are the output state which are named as a next state, which we get after applying the inputs. This is our case 2, this is our case 3, and this is our case 4, which we have discussed already. For S0, R0, output will not be changed. For S0, R1, the output will be in reset state. For S1, R0, output will be in set state. And for S1, R1, output is in rest state, rest condition, so that should be avoided. Therefore, in comment it is written as prohibited state. So this is how we learn SR latch using NOR gates. For homework, you have to write the SR latch using NAND gates, in which we have to write the circuit description and operation with all the 4 cases, and lastly the truth table. This you have to submit by tomorrow evening, that is on 24th November. Thank you.